Okay, good morning, everyone, and welcome to the third in the FutuRaM webinar series, where we're presenting some of the results of the project. Today, we're going to talk about unlocking critical raw materials from WEEE, and we'll give some insights that we've had from the research in the FutuRaM project. So thanks, everyone, for attending. Some quick housekeeping before we get into the main part of the webinar. Just a reminder, it's being recorded today, and please, everyone, keep your microphones muted. Questions will be answered at the very end of all the presentations, but please add them to the Q&A. There's a Q&A button on the top menu bar, or the chat, either one of those, and we'll get to those at the end of the presentation. Okay, just to introduce our speakers, we have Giulia Iattoni and Sarah Bataushi from the United Nations Institute for Training and Resources, and we also have Katarina Kippert from the Technical University of Berlin. All have been prominent researchers in the project. So quickly before I pass on to the main presentations, a short introduction to FutuRaM. So it's a Horizon Europe funded project set against the geopolitical uncertainty, the accelerating energy and digital transition, and the need for better data on critical raw materials in Europe's waste streams. And the approach we took in FutuRaM to create this better data. Initially, we established what is in the urban mine by assessing its composition and the quantities there. And we've done this for 7 different waste streams. So e-waste, batteries, end-of-life vehicles, construction and demolition waste from buildings, wind turbines, slags and ashes, and mining waste as well. And one of the new approaches we developed in the project was the development and use of a recovery model, and this enables estimates regarding the quantity of secondary raw materials that could be extracted from the waste stream. So we're looking at the recovery processes, what is realistically and practically possible to extract from the waste generated. And some of this data is presented in the Urban Mine platform. Hopefully you've all had a chance to visit the Urban Mine platform. The link will be available later in the webinar. We also developed scenarios in the project. So we developed 3 different scenarios and projected these to 2050, incorporating a life cycle assessment as well. And these scenarios were business as usual, where things carry on as normal with a slight increase in circularity. A recovery scenario where steps are made to improve waste management and improve recovery of raw materials, and circularity, where there's huge steps made towards a circular economy. These scenarios enable us to test the impacts of different conditions on future quantities in the waste streams. And we do this to 2050, and again, that is presented. In addition, we also adapted the United Framework Classification for Resources for use in secondary raw material projects. It was developed for primary raw material projects, and the project established a framework and a tool to enable this to be applied to secondary raw material projects. And we've tested this in 20 different case studies at national and project level across the 7 different waste streams. And of course, we're doing this because in the hope that it contributes to a better secondary raw material and critical raw material management in Europe and knowledge in Europe. And indeed, that's already happened. We have contributed data from the project to assist with the implementation of the CRM Act already. So we've already taken a step. It's making a difference in the project, and we hope it continues to do that and has big impact in the future. Okay, so without further hesitation, I will pass to Giulia, who will begin the main part of the presentation. So over to you, Giulia.
Thanks a lot, James. I start to take control. Can you see the slide moving?
Yeah.
Yes, perfect. So again, thanks for the introduction and thanks to all the participants for the interest in the FutuRaM project and in the results for WEEE. In particular, this first part of the session will cover the stock and flow and the recovery modeling for critical raw materials in WEEE, with an overview on the methods and on some key findings. First, what's the background where the FutuRaM project is moving? The European Union is aiming to strengthen the resilience of raw material supply chain in order to enable the green and digital transition. And a key objective is to reduce the current overdependence on third countries. And to achieve this, the EU is promoting increased domestic production of both primary and secondary raw materials through recycling, with a strong focus on critical raw materials. Although the Critical Raw Materials Act was adopted after FutuRaM was launched, the project remains strongly aligned with the core objective of the Critical Raw Materials Act, thanks to a close collaboration and exchange that we had. So within this background, we immediately faced two challenges. That before FutuRaM, there was no structure and harmonized knowledge on availability and recoverability of strategic and critical raw materials from WEEE, and there was no central knowledge base available. So the two main goals and outputs also of FutuRaM are: first, enable fact-based decision-making for secondary raw materials management in the EU 27+4 through developing knowledge on the availability and recoverability of secondary raw materials within the EU, with special focus on strategic and critical raw materials from now to 2050. And second, disseminate this information through a secondary raw materials knowledge base accessible to everyone. Today, we are focusing on WEEE, and we start with an overview on the methodological framework developing FutuRaM, going step by step. As a first step in the FutuRaM methodology, we developed the product composition for 54 different electrical and electronic product groups, following the UNFC's classification. The composition data was built according to a hierarchical and nested structure where we start from the product level. We identify the components embedded, the materials embedded in those components, and the elements embedded in those materials. And each layer is linked and mass balanced to the upper and to the above one. The data for this was obtained from the product sampling of recyclers and PROs, and also from literature. So this is just to provide you with an idea of how our composition data structure, where you can see the main components, the material fractions and elements, including critical raw materials that were identified. And this is an example for a laptop, which is UNIKEY 0303 and part of the category screens and monitor. Then we apply a stock and flow model to quantify the three main indicators of e-waste statistics: placed on the market, stock, and waste generated. We then apply a sales lifetime approach, quantifying first the amount of products that are placed on the market, starting from the trade and the domestic production statistics. Then we apply to that a lifetime profile to derive the WEEE generated, and consequently also to calculate the products in stock. The stock and flow model is applied to a long time series, and it is strongly rooted to the principles of the official e-waste statistics. Out of the amount of the WEEE generated, then we know that part is collected compliantly with the legislation, while part is destined to other complementary flows. For example, it can be mixed with other plastic waste or metal scrap, and usually undergoing substandard recovery treatments. It can also be mixed with the residual solid waste. It can be exported for use, or can also have an undocumented fate. And data for this flow mapping was obtained mainly from Eurostat, from the key figures collected by the WEEE Forum members, and from the available national studies. Through the stock and flow model applied, we can then derive the composition of the waste, which maintains the same hierarchical and nested structure as the product composition, but it is not anymore at product level and rather aggregated per WEEE category as defined in the WEEE directive, so with the 6+1 categories of the WEEE directive, and also considers a shift in time, meaning that the composition of the waste in, let's say, 2020 will be based on the composition of products placed on the market in previous years, from 2010 or 2015, for example, depending on the type of products. And this is just an example of the composition data for category 2, screens and monitors, where you can see the main components constituting the category in the inner circle, the materials fraction in the mid circle, and the elements in the outer circle. But we have the same type of analysis for all categories of the WEEE directive for each year and each country, also in the scope of the project. Then the last step of the methodology was to quantify the amount of secondary raw materials recovered and lost during recovery, and this was done through a recovery model that was developed in FutuRaM. In the recovery model, we could map and quantify the flows throughout the main treatment processing using data from the producer compliance scheme, from recyclers, and from literature. We mainly looked at the components and material fraction which could be obtained as output from the first part of the treatment chain, including pre-treatment, such as manual separation and dismantling, and then shredding and mechanical separation with primary and secondary treatment. This is just an example for the copper content, which you can see highlighted in green in category 2, screens and monitors, and is a simplified flowchart just to provide you with the idea behind the recovery model. Then the entire FutuRaM methodology was applied for 3 different future scenarios because we are looking until 2050. The business as usual scenario, where the current trends are being continued. The recovery scenario, which is characterized by improved waste collection and recycling, and the circularity scenario, which together with improved waste collection and recycling, as in the recovery scenario, also implies reduced consumption, which means less product placed on the market and also less waste generated eventually. So as outlook to 2050, we could see that the WEEE generation increased from 8 million tons in 2010 to 10.7 million tons in 2022. And this is projected to grow at an accelerated rate under both the business as usual and the recovery scenario, reaching 19 million tons in 2050. In contrast, we can see also the circularity scenario, which is projected to result in a lower WEEE generation of 12.5 million tons. And this decline is mainly attributed to products' lifetime extension through reuse and repair and to a reduced consumption, which are the main assumptions under the circularity scenario. All WEEE categories are expected to increase by 2050, except for screens and monitors, which is decreasing mainly due to cathode ray tubes monitors disappearing from the WEEE generated flows, and also to a general lightening trend of devices. And PV panels are expected to experience the most significant growth, rising by more than an order of magnitude, while the market looks to remain stable for lumps. The total WEEE generated in 2022 contained 28 strategic and critical raw materials, each present in quantities above 1 ton. And this equated to 1 million tons of critical raw materials in total present in the WEEE generated in 2022, which is projected to grow to between 1.2 and 1.8 million tons by 2050, with the as most abundant elements being aluminium, copper, silicon, and magnesium. The CRM content from WEEE is projected to increase looking in 2050 in most cases. However, there are also some significant declines to be mentioned, and this can be observed for some critical raw material. This is the case, for example, of antimony, which is present in CRT that are being phased out, while it remains in use in other types of application, such as in printed circuit boards. Decreases can also be observed for rare earth elements like yttrium, cerium, lanthanum, europium, which are contained in fluorescent powder of fluorescent lamps, which are being phased out as well of the market. Having now a look at the WEEE management in the U27+4, out of the 10.7 million tons of WEEE generated that we saw at the beginning in 2022, only 5.7 million tons, equivalent to 54%, were collected and appropriately treated in a compliant way, meaning in accordance with the EU regulations, such as the WEEE directive. These volumes were collected through retailers, municipal collection points, and commercial collection companies. Following WEEE treatment, approximately 0.4 million tons of critical raw materials could be recovered, including, among others, 160 kilotons of copper, 200 kilotons of aluminium, 12 kilotons of silicon, 1 kiloton of tungsten, and 2 tons of palladium. And also some precious metals such as gold and silver, alongside with steel and other ferrous materials, could be recovered too. And here it is important to specify what is meant by critical raw materials recovered. In FutuRaM, this term refers to the critical raw materials, which are part of material fractions and components classified as secondary raw materials, which are the output fractions of the first treatment stage, meaning dismantling and mechanical treatment, and are then subsequently sent for further recycling, processing, or recovery. This means that part of this quantity will be functionally recycled at elemental level or made available for further processing, while another part will be dissipated into residues, and we cannot distinguish between these two quantities. This is because not all critical raw materials that are present in the secondary raw materials are technically or economically recoverable. There are barriers or enabling factors that should be considered, and you will hear more information on this in the next part of the session. And also, despite the compliant collection and treatment, still 0.1 million tons of critical raw materials could not be recovered and went lost during the treatment process. This is mostly consisting of rare earth elements like neodymium, dysprosium, yttrium, europium, which are important materials found in components such as permanent magnets, fluorescent powders, and other type. Out of the 10.7 million tons of WEEE generated, the remaining 46%, which means about 5 million tons, was not compliantly collected or treated, increasing the chance of losing valuable material. And the largest quantity of this falls under non-compliant recovery, including WEEE that is mixed with other metal and plastic waste, where only some materials such as iron or steel may be recovered, but often also at lower standards. Then another part is discarded with the residual solid waste and sent to landfill or incineration. A fraction is exported for reuse, and the remaining share remains undocumented, likely either exported illegally or processed through informal or unregulated channel. And this led to 0.5 million tons of critical raw materials being lost even during the collection phase. Just to showcase an example for one critical and strategic raw material, which is present in large quantities in WEEE and is mostly recovered with the current management system, copper can be found in many WEEE categories, and especially in small equipment, large equipment, and temperature exchange equipment. While in terms of components, that's the case for printed circuit boards, cables, inductors, and compressors. That's just an example, but we have the same type of analysis for all strategic and critical raw materials. And here you can see the amount of copper recovered in secondary raw materials and lost during collection or treatment in the U27+4, both in 2022 and in 2050 for the different scenarios. In 2022, around 170 kilotons of copper were recovered, while more than the same amount was lost during either the collection or the waste treatment phase. And by 2050, assuming higher collection rates, improve separation of the copper-rich fractions, and enhance recovery processes, the annual copper in secondary raw materials is projected to reach between 300 kilotons and 500 kilotons, depending on the scenario considered. Looking now at neodymium, which differently from copper is a critical raw material which is present in much smaller quantities but has still an untapped recoverability potential. This can be found mainly in permanent magnets and are drives from large equipment, small AT, and screens and monitors. And even though it's present, recovering neodymium from WEEE is still technically challenging and not widely implemented at a large scale, mainly because the quantities are lower, the components are small, dispersed, and often not easily separated. In 2022, there were only around 30 tons of neodymium in secondary raw materials from WEEE in the U27+4. The majority actually went simply lost with the WEEE, which was not even collected in first place, or during WEEE treatment. And in the business as usual scenario, the current picture doesn't change so much to 2050, while in the circularity scenario, with improved collection and recovery technologies, more neodymium can be recovered than in the business as usual. And besides that, there is also less waste generated and therefore less losses of neodymium. The recovery scenario increases the amount of neodymium recovered, but it also comes with a higher total amount of waste generated, which leads to higher losses of neodymium overall. So some key takeaways that we can take for now are that the WEEE generation is increasing rapidly under the business as usual and the recovery scenario, and this growth can be reduced only through a lower consumption and demand and longer product lifetime. By 2050, all WEEE categories are expected to grow, except screens and monitors, with photovoltaic panels showing the strongest increase and becoming a key silicon hotspot. In 2022, the WEEE generated contained a total of 1 million tons of 28 critical raw materials, but only 54% of this WEEE generated was formally collected, which means that almost half of the CRM content got lost during the collection phase. The critical raw material content in WEEE is mainly attributed to aluminium, copper, silicon, and magnesium, but there are many others present in smaller quantities. And most of them are expected to increase toward 2050, except those which are present in products being phased out of the market. Improving the availability of these materials requires better collection and recycling, but also less waste generation overall, which means less consumption. And very important, the presence of certain critical raw materials in WEEE does not necessarily imply that they are technically or economically recoverable. And this depends on the presence of some barriers and enabling factors that have to be considered. And you will hear more about this in the next part of the session. Now I just gave you a snapshot of some results that we're having for some critical raw materials, but if you're interested in more detailed data, also for other critical raw materials, I invite you to consult the report that we published for the International E-Waste Day in October 2025. Then today, one thing that I wanted to highlight, we are focusing on WEEE, but if you're interested in the results for other waste streams covered under the FutuRaM project, which are many, 7 different ones, then you can consult the UrbanMine platform, which is the app where we are publishing the FutuRaM results. This was launched in November, and it is now available for the public. You can also consult the FutuRaM Zenodo repository, where we are publishing all the milestones, deliverables, and dataset in detail. And I indicated here also those resources which are mostly related to the content of the slides that you just saw. And there is also the upcoming FutuRaM final report, which will summarize the main results, the insights, and the recommendation arising from the project. The expected publication date for this is May 27. So I also invite you to stay tuned for that. I thank you again for your interest, and I'm leaving now the floor to Caterina for the next part of the session. Thank you.
Thank you, Giulia. I take over the slides. Just a quick check. Does it work?
It does.
Yes. Okay. Nice. So also welcome from my side to everyone participating. Besides what Giulia already presented, the modeling we did and the quantitative estimates of secondary raw material, we wanted to also assess more in detail the recoverability of especially critical raw materials. And I will now present shortly how we did this and some results for the WEEE waste stream. So there are different recoverability assessment standards available. So we have, for example, the EN 45555, which is for energy-related products, or we have the IEC 62635, which is for electrical and electronic equipment. But these standards, they are focusing on product recoverability. But what we wanted to do in FutuRaM is we wanted to focus on critical raw materials. And what we did here is we considered the application of critical raw materials in a product. So where and how are they used? Because this has a big impact on the recoverability. And we considered the end of life scenario of the product. With this assessment, we wanted to answer the following questions, like in which applications do the critical raw materials have high or low recoverability and why? And what are the main enablers or enabling conditions and barriers for the recoverability of these critical raw materials? To set this in the context of FutuRaM, I will present you a short figure, a small figure. So we have that square, let's say, of collection and recovery. We have waste that is we have waste that is collected. It's a part of the waste generated, and we have something that is in use or stock, which is not touchable for the recovery. Then we have waste that is not recoverable. We have recoverable waste and recovered waste. So what Giulia just presented and what was modeled is what is currently collected and recovered. What we also modeled is what is in the future collected and recovered. Both was done in a quantitative assessment of the secondary raw materials with the recovery model. And for the future, it included the 3 different scenarios that were mentioned already. What we additionally have is a recoverable potential. So it is not recovered, but it could be if certain barriers are lifted. We have something that is collected but not recoverable, then not collected and not recoverable, and the rest which is in the stock. What we did now with the recoverability assessment, which is only qualitative, so not quantitative, we checked for specific critical raw materials and specific applications where in these boxes they are located. And just to complete the whole picture, what we did in the FutuRaM as well is the UNFC application to specific case studies, which we'll present it in the 3rd part today. So how we did this specifically, we developed this big table, and I want to zoom in now in the different parts of this table. So at the top, we have the CRMs and applications that we want to that we want to assess or evaluate. We identified the critical raw materials and the applications, for example, what Giulia already mentioned, neodymium and permanent magnets in motors or speakers or some other components, and selected the, let's say, most important critical raw materials. So because there's a big amount of critical raw materials in all the waste streams and especially in WEEE. So we decided on what is the most important. Then all these combinations of CRMs in applications, they were assessed for their recoverability according to 5 different according to different criteria in 5 categories, which included the design, the waste flow, technical, economic, environmental, and legal criteria. The whole concept is based on a project called Upgrade, where I also put the link in the corner here. At the end, the results looked like this big table on the left side. So for we assessed 32 applications of critical raw materials, and you can find all the results of this assessment in the report mentioned here, Extended Waste Stream Composition Assessment to enable secondary raw material assessment, which is available on Zenodo. And now I want to just highlight a few of the results. So a snapshot of what you can find in this table and also the report. So one example is the aluminum, copper, and magnesium in WEEE, which is mainly present in casings, frame, in heat sinks, but also in cable and wirings. So what we identified that what are more the enabling conditions are that components have high mass fractions of these critical raw materials, and these components are oftentimes easy to dismantle or to sort after shredding. There are advanced sorting technologies available with eddy current, XRT, LIPS, or XRF. And the recovery infrastructure is really established for aluminum and copper. What is on the barrier side is that we have alloy-based sorting is really relevant, particularly for aluminum. Otherwise, we will have problems with downcycling and surplus scrap. And there's still only a weak recovery infrastructure for magnesium alloys. Another example that we assessed are the printed circuit boards. Here we have multiple critical raw materials included, which are like tantalum in capacitors, gallium, cobalt, and scandium in integrated circuits, antimony as flame retardant, and solders, the tin and solders, then precious metals, tungsten, and copper as the main conductor. What is an enabler here is that PCBs can be visually identified and are dismantled when they have a high value, which is practiced, for example, for laptops. Dismantling is also required by the WEEE directive if they are larger than 10 square centimeter. And there's a really established infrastructure to recover copper and precious metals from PCBs in integrated copper smelters. They can also recover tin and antimony. Then what is like, let's say, in between enablers and barriers, we have certain parts that contain critical raw materials in very high mass fractions, for example, the 40% tantalum and tantalum capacitors. But it's necessary to remove them before recovery. Otherwise, the tantalum will be so diluted that it's not economically recoverable anymore. This barrier side includes the complex structure that we have in PCBs, that certain critical raw materials occur only in trace amounts, and PCBs with lower value are not dismantled, and then they get shredded and the critical raw materials are lost. So I come to the last example, which is gallium in LED chips, or europium or yttrium in LED and fluorescent phosphors. Giulia already mentioned that the amount of rare earth elements is declining, which is also due to the phase out of the fluorescent lamps, because they contain up to 20% of the rare earth elements, but the LED, on the other hand, they contain much less quantities of rare earth elements. And if they should be, if the aim is to recover these rare earth elements, then it's necessary to remove and concentrate these LEDs. Another problem is that there's still a rather low correction rate of lighting equipment. There's no automated separation of LED backlights, which are a big part of the LED application. There are recycling conflicts with precious metals and copper, and also even for the phosphor powders from the fluorescent lamps, they can be extracted, but the processing method is still under development. Then I come to the conclusions. So what is really important for the recoverability is that components are identifiable, accessible, and removable. Miniaturization and complex assemblies pose challenge for this. To ensure the functional recycling of the critical raw materials in alloys, we need advanced sorting technologies, for example, LIPS or XRF. The integrated copper smelters enable the simultaneous recovery of different CRMs, including copper, precious metals, and other byproducts like tin and antimony. The recycling infrastructure must be scaled up to handle increased volumes of critical raw material-rich waste streams, for example, the permanent magnets and the silicon from PV panels, both expected to increase in the future. And last point, some critical raw materials remain inherently difficult to recover with the current technologies. So we have, for example, the gallium, scandium, and rare earth elements in LEDs or other trace elements, which are simply really difficult to recover due to their low mass fraction, dispersion, and the complex matrices. So thank you for listening, and I will hand over to Sarah now.
Yeah, thank you very much, Caterina. So let me see if I can. Can you see the slide moving? Yes, right? Yeah. Okay, great. So now we will introduce, let's say, the third and also the last section of this webinar, which is more into the real-world applications, because we will look at the UNFC case studies at national level. As it was introduced at the beginning from James and also from Giulia and Caterina, the UNFC case studies were developed in the project for different waste streams, but today we will see only the e-waste example. I'm not sure how many of you are familiar with the UNFC, but basically the UNFC stands for the United Nations Framework Classification for Resources, and it is an harmonized, global and principle-based classification systems that it was historically used for the mining sector to precisely classifying primary raw material. While in the FutuRaM project, what we did, and so the novelty of the project was somehow to kind of test the applicability of the UNFC also to the quantification of secondary raw materials. So material coming from the treatment of specific waste streams, such as the waste stream. The project has developed different UNFC case studies at both site-specific but also at national level. And for concerns the e-waste, the site-specific case studies was carried out by WEEE, which is a company in France. But we will not go into more details in this, but if you are interested in knowing more, you are more than welcome to check the link in the slide that is part of the Zenodo repository that it was also shared in the chat. Today we will focus on the national level example because we're the one that we at UNITAR SCYCLE were responsible of. We have run 4 different WEEE national case studies in 4 different countries, which were Austria, France, Italy, and the United Kingdom. More precisely, we at UNITAR SCYCLE, we have closely collaborated with 3 other project partners of the project, which were Ecosystem, Arion, and Ecogenesis, who helped us gathering data for France, Italy, and the United Kingdom. And together we have kind of applied a bottom-up approach, and so because we mostly use statistical and also aggregated data. On the other hand, the Austria case study was developed by the Australian Environmental Agency, and what they did was to apply a bottom-up approach because they were able to collect more primary data directly from treatment operators. And today, of course, we will focus on the top-down examples because, again, we're the one that we at SCYCLE have conducted. Just a couple of words on the theoretical framework, because as said, the UNFC was originally applied for classifying primary resources, but what the project did, and in particular the coordinator of those activities, which was LMU, we have kind of customized such UNFC classification also to a more national context, and so to different kind of data. And so we kind of introduced a new UNFC compliant classes rate. And you can see the list of the UNFC compliant classes in this table on the left-hand side. And so we, as case study developer, has used this different and new theoretical framework as a reference guide. But let's jump now into the e-waste example, because the objective, as said, it was to test the applicability of the UNFC also to the quantification of secondary raw materials. But more precisely, what we wanted to do, it was to map and also quantify specific output fraction obtained from the treatment of specific e-waste collection groups. And indeed, we have analyzed the copper fraction coming from the treatment of the collection group small equipment, and then we have analyzed the aluminum fraction from the treatment of screens and monitors, and then the ferrous metal fraction from the treatment of temperature exchange equipment. The choice of the output fraction and on the e-waste collection group was simply driven by the data availability, but also the data quality across the 3 different countries for the same year to allow a sort of potential comparison. Moreover, we have also analyzed and we received some data on the recovery rate of specific element fraction, such as copper, palladium, gold, silver, and tin, from the treatment of printed circuit boards derived from the collection group small ET and telecommunication equipment. As said, the geographical boundaries, let's say, were the 3 different countries, so France, Italy, and the UK, while the temporal coverage was the year 2022 that it was used as a reference year. And to complete the system definition, let's also say that our system boundaries went from the devices and the product that were placed into the market in the year 2022 until the first pre-treatment of the recycling processes. And so the system boundaries went from the POM amount until the generation of the output fraction from the treatment of specific e-waste collection groups. And how did we build all of those editing up? And so how did we actually perform our calculation? Well, basically, we have initially started by using the results that the project had already developed and that were already present across the project. And in particular, I'm referring to the composition data that it was already produced and present in the project. And we linked the composition data to the stock and flow model that it was, again, already available in the project and it was before presented by Giulia. Within the stock and flow model, we were focused on the e-waste generated, and from that we have extracted and we were interested in the amount of e-waste that were compliantly collected. Because from the amount of the e-waste compliantly collected, we have linked it to the end-of-life scenario. And so at that time, in that stage, we were somehow able to account and quantify the output fraction generated from the treatment of those e-waste collection groups that we have identified at the beginning. Moreover, we have also added an additional qualitative information, let's say, because once we knew the output fraction generated, we were also interested to know the destination of those output fraction. So we wanted to know whether that specific output fraction would have been treated domestically and so recycled in the same country where it was generated. And once we had all those information, let's say, developed and we merged all of those building blocks together, we were then able to kind of apply the UNFC assessment and so to assign a specific UNFC compliant class rate. In particular, for a few words on the data availability, because of course all the data that we have used until the end of life, as said, were already results of the project, while the end of life was something that we needed to model in the context of the UNFC case studies. So for the component and the material fraction, we have used data coming from reporting systems such as RepTool. Then we have also used a few other data derived from other activities in the project, for instance, the recovery model, but also the recoverability assessment just presented by Caterina. And also we have used data coming from some questionnaires that we have distributed to treatment operator via our project partners. And then we have somehow grouped all those data sources together, and we were able to ultimately quantify the output fraction amount from the treatment of those specific e-waste collection group. And this, for instance, is the example of the mass flow analysis that was built with the example of the copper fraction derived from the treatment of small equipment for the case of Italy in year 2022. So once we have the MFA built and represented also in a form of a flowchart, which was the most useful kind of representation in this contest, we added the last stage, which was assigned to each of these different flows a specific UNFC compliant class rate. And so we were able to say whether a specific flow would have been rated as viable, non-viable, or potentially viable. Similarly, we also did the same for the element fraction data, but with the big difference here that we didn't receive any element fraction data from reporting system or from treatment operators, simply because there were not. And so we gather and collect element fraction data through some laboratory tests that our project partners in the UK were able to process and to run. And so we ended up also analyzing the copper, the palladium, the gold, silver, and tin derived from the treatment of PCBs from the category small IT and telecommunication equipment. In this case, again, we have built our MFA, and thanks to the help, let's say, of the MFA represented, we were then able to apply the last stage, which was, let's say, we assigned to each of these different specific flows a specific UNFC compliant class rate. To conclude, we can actually say that applying such a kind of UNFC exercise, this shed light somehow on few still existing challenges of the e-waste recycling system, because on one end we have the data limitations in the sense that, of course, we have analyzed 3 different countries that had similar reporting system, but there were still few differences. And so our work was also to try to harmonize those data that we gathered. And also, more importantly, we also noticed the very lack of, let's say, of critical and strategic raw material recovery data reporting. So if we want to, let's say, extract a recommendation from this exercise, it would be to maybe aim to have a more harmonized and shared European reporting system that is also able to account for critical and strategic raw material recovery data. Secondly, the other aspect that was interesting to notice, it was also the somehow cross-border dependency in the countries in Europe, in the sense that also mapping those destination of the output fraction was quite clear to see that a specific output fraction generated in a country, it is likely to be treated and recycled in another country, but still remain in Europe. So a recommendation in this case, it would be, if we want again to apply a UNFC assessment at national level, maybe it would be better and more coherent to expand the geographical system boundaries to the European coverage, to instead of only focusing on the national border, to somehow allow a more realistic, let's say, picture of the reality of the e-waste recycling sector. And with this, also this part is concluded, and I think I will give back the floor to James, I guess. Thank you very much.
Okay, thank you very much, Sarah, and thank you, ladies. Very interesting presentations and very informative too. Before we move on to the Q&A, just quickly, just to some of the things we've referenced during the presentation. So there's further information on the FutuRaM website, the Urban Mine platform. Have a play with that. That's the URL for that. These should all be, you should be able to click on these links. And if you want to stay informed of what we're doing, please register via the Get Involved. The 3 email addresses there as well for the presenters today. Questions. We had a couple in the Q&A. one of which Giulia has answered, I hope satisfactorily. There's another one regarding the currently unused recycling potentials, which would be the low-hanging fruits. I assume it's the low-hanging fruits from which CRMs could be extracted from WEEE. So I guess this is in the perhaps the recovery model, maybe the recovery assessment. Is there anything there that looks like a low-hanging fruit? I'm not sure if we actually did assess that, but Katerina, if you want to answer that.
I already answered the question, I think. So we identified, for example, the ND-FeB magnets in larger components with a high recoverability, especially with the upcoming regulations and this short loop recycling potential. Also, they have a really high REE mass fraction, rare earth element mass fraction. Then silicon and PV modules is another interesting case, also because PV panel waste and will increase in the future due to the energy transition. And maybe something a bit unexpected, but antimony as part of the flame retardants could also be interesting because it occurs together with bromine, and bromine content is limited in plastic recycling. So if this is separated, also the separated fraction is enriched in antimony and could be extracted together.
Excellent. Okay, thank you very much. I hope that helps you, Maximilian. Any other questions? Yeah, we've got a hand raised, so we will take some questions verbally. So go ahead, Fernando.
Yes, hello, good morning. Thank you very much for all the nice presentations. I have a question. I have my camera off because my connection is really low here today. But I have a question also related to the last comment. When you say that was select the most important, I was curious about which criteria you use, because okay, some are like relate to mass, but some tiny milligrams material could be very important as well, right? In few components and technology and sector. So how did you solve this issue?
So there was no standard method applied for all waste streams. So every waste stream decided, like they had their own method on how they identified the most important CRMs or applications. And for we used the result from the modeling, from what Giulia presented. We used the composition data, and we used the screen fact sheets particularly. So in where we is an important use, how it's called, sector. Yeah, so, and there was also some literature used. Yeah, many information was assessed, and based on this.
Yeah, okay. Yes, because this is very tricky, because I was digging on this problem, and okay, I was just curious, because and then you can have like the criticality of each component, what the supply risk of each one, but then it doesn't mean that they are the risk one in the electronics, right? So it could
True,
be
yeah.
like, and then you have the mass and so on. But okay, thank you very much. I'm gonna dig in your files and see what we can get from that as well. Thank you.
Thanks, Fernando. There is also a question in the chat. So a question about whether electrolyzers to produce hydrogen are within the WEEE directive scope. I don't know if Giulia, you know this.
Not that I'm aware of, to be honest, and we didn't cover this product in FutuRaM, so this should imply additional research, I'm afraid.
Yeah, I don't know if you want to elaborate, the person who wrote in the chat, just elaborate a bit on that, just to help us understand what they are, what this equipment is. No, okay, that's fine. Damir, you have your hand raised.
Yeah, hello James. Firstly, thank you for the great presentation to all of the presenters. Just one quick question. I'm checking now on the Zendo data, different, searching for it. Do I understand correctly that the composition data, so how much, what components are in different UNO keys or categories, this is and will be public, or am I mistaken?
On category level.
On category level.
Yes.
Okay, and for we have this, so just to know that I can spend a bit more time to get this data, because this is really, really valuable data if we could get it.
Yeah, you can find it partly on the Urban Mind platform, combined with the quantities, and also on Zenodo, we have the data set separately.
Yeah. Perfect.
Okay, thanks, Damir.
Maybe, James, I just saw a question in the chat, in the question and answer, sorry,
Okay,
section. I can address, it's asking whether we consider the population in the projections of which generation. The answer is yes. We consider the projections of population, but also of purchasing power parity, so the economic dimension. And this is being done using some forecast available at Eurostat and also at OECD. In the resources that we linked, there are also more information on the data sources used in that sense. But sorry, I just saw in the Q&A and I wanted to address.
Yeah, there's actually a couple more in there as well. And so you've answered the one about future scenarios and population size there, haven't you? Do you see any potential for improved sorting or recovery of materials in the future, for example, through new technologies? Any new materials that could be recovered in addition to what is already getting recovered? So again, that's about recovery and
Yes,
the assessment of new technologies. Sorry, go ahead.
Yeah, no, in our model, we try to assess the technologies which are already available and established, let's say, but we also consider those that are emerging. So we assumed that these will become more established in the future, looking at the time series and the time span that we are looking at. So this is also taken into account in the modeling that we did from the recovery side. I don't know if Katerina wanted to add more detail, but this is also considered.
Yeah, especially for the recovery of critical raw materials as alloying elements, for example, in aluminum, the improved sorting is something really important. So we think that LIPS or XRF will be more established in the future. So they are already, I think, getting more and more popular.
Okay,
Yeah,
thanks,
and
Pablo. Sorry, but I think the person asked the question, Pablo, has his hand raised. Maybe wants to elaborate slightly. Yeah.
Yeah, thanks. Yeah, it's super interesting. I was wondering, I haven't had a look at the report in detail yet, but is it possible to see what kind of technologies you considered in detail to really evaluate these technologies or see what you considered there?
I think they are available in a milestone that I'm not sure if it's still yet public on Zenodo, but it should become because it's a milestone under Work Package 2. I don't remember exact milestone 17 maybe. So maybe we can check if that's available and we can also get back to you.
Perfect, great, thanks. Super interesting.
Thank you.
Thanks, Pablo. And then there's another question in the Q&A from Roman. Very important CRMs are available in small quantities, but they have very low value. What is the recommendation?
Sorry.
You go on.
Can you repeat, James, because I was writing down?
Yeah, it's in the Q&A, so
okay.
if you can read that. But it's about, I think it's about some CRMs being in very small quantities and having very small, very low
high
value
value,
because
I
of
think.
that. Well, I think there may be high value per
Yeah.
kilo, but small value in total, perhaps.
Yeah.
Roman's turned his camera on. Maybe
Perhaps
you can
I can
expand slightly.
explain a little bit. We have done a study about gallium in LEDs. Gallium has no value, economically value, and is available in very low quantity, but it's an important serum. Do you already found some recommendation what to do? Because that's a bigger problem. With a lot of CRMs, they have no value and they're available in small quantities. And a lot of them, without only copper, aluminium, and some other main metals are valuable. And all the other ones are not valuable. That's the main problem we face in operational recycling.
Yeah, in the recoverability assessment we did with the barriers and enablers, then in this case, if, for example, mass fraction is super low and value is super low, that was indicated as a barrier. What we wanted to identify in this task is if, like, for example, barriers are in like concentrated, let's say, in one specific category. Like if it's always, for example, the value, or if it's more the technology or something. So if we can see, for the CRM and this application, the only barrier, let's say, is the value, maybe we can do something about it. But if there's a lot of different barriers as well, okay, maybe that's not the one to focus on. So that was, we considered it somehow, I would say. But it really depends on which CRM and which application. So there's no general answer, I would so say, to this question.
So unfortunately, the low-hanging fruits are not so hanging, not so low, huh? Unfortunately. Okay, thank you very much, ladies.
Thank you, Roman. There's another question before I come to you, Fernando, sorry. There's another question in the chat. Unless, Fernando, is it to address that recent conversation?
Yes, it's kind of related. Thank you. It was just like I was just wondering if for the recoverability, if you also consider the thermodynamics of the metals. I know it's a topic that it's kind of controversial, like from Marcus Ruto, that he's always advocating to us, like the scientific community, to check the thermodynamics of the XRG, of the recoverability. I'm just was curious if you have this in consideration at some point.
I'm not 100% sure if I understood the question completely, but of course we also know that there are thermodynamic limitations of the recovery, and yeah, that is considered, but we have to say we didn't model the smelter step, so that part of the recovery is outside the scope of the modeling.
Yeah, okay. That can be very important, just a comment. I remember I was working in another project of recovering of permanent magnets from WEEE. And in the smelter, we had like loss of 40% of the neodymium magnet. This is direct from the, let's say, from the industrial unity. I'm saying because I was dealing with the data. It's not published, but so yes, there are a lot of let's say critics related to this from especially from Marco Rutter. I guess most of us might know his work on the wheel of metals as well, wheel of recoverability. I think it's something interesting to look into that as well.
Thanks,
you.
Fernando. Thank you. Final question then, there's one in the chat. How would you suggest prioritizing the recovery of one CRM over another, or going for the easier option to recover? Giulia, so you've answered it just now in the chat.
I was replying.
Okay. Thank you. Well, I think that's that's a good moment to finish. Just quickly, before the end, just to let people know that there will be our final event for FutuRaM will be on the 27th of May, and that will be held at the Novotel in Brussels city centre. The registration is open for that event. There's a link in the chat here, so we would welcome you attending that for further conversations, further questions. We'll have the opportunity to discuss things in more depth during that particular event. So please register. It's a free event, of course. We'd love to discuss the project with you and next steps and all the results from the work we've done over the last 4 years. And I think the next, quickly scroll into there we go. Further information about our final event is there. So thank the speakers from today and thank everyone for attending. It's been well attended again as this webinar, and we look forward to keeping in touch and hopefully seeing some of you in Brussels at the end of May. So thank you very much and have a productive rest of the day and week.